Hello and welcome to the first video on A-level proofs and explanations. So we're looking here at something called the contrapositive, in particular how we can prove things using the contrapositive. I've left this outside of the main A-level notes for edXL because technically this isn't in the specification. You don't need to know this. Which might beg the question, well, why am I mentioning it then? Well, since you do need to know about proof by contradiction, and that the contrapositive is a nice extension idea to certain proofs by contradiction, it may well pique your interest to explore this idea of what the contrapositive is and when it might be useful, just in general. And again, if you do go on to study maths at university, then it might well crop up, so knowing it in advance couldn't hurt. So first of all, I'm going to explain what it is, what the contrapositive means, have a look at some examples, and I'm also going to prove that an implication and its contrapositive are logically equivalent. So let's get started with a few ideas. So proof by contrapositive. So the contrapositive of the implication A implies B is this. Now this symbol here, which looks like a bent-in line, means not. So the contrapositive of A implying B is not B would imply not A. I've just explained here that this symbol means not B and this here means not A. So if the implication that A implies B is actually true, then we can prove that its contrapositive, not B implies not A, is also true. On the other hand, if the implication that A implies B is false, then its contrapositive, not B implying not A, is also false. So for that reason, an implication and its contrapositive are logically equivalent to one another. And we're going to explore and have a look at why this is the case in just a few moments. Before that though, let's have a few examples to illustrate what this contrapositive means with a few contexts. So first of all, a mathematical context. Consider this statement. So statement A, if n squared is odd, then n is odd. Compare the idea of the implication and the contrapositive. So A and B switch orders, and A is replaced at the end with the opposite of A, and B is replaced now at the beginning with the opposite of B. So here, n squared is mentioned first, then n is mentioned last. So in its contrapositive form, n will come first, and then n squared will be mentioned last, and they'll be made opposite. So n squared will now be even, and n will be even. So putting that together, the contrapositive of A is that if n is even, then n squared is even also. We don't have to limit ourselves to simply mathematical contrapositive statements either. So consider this statement B. If it rains, then I wear my coat. So rain's mentioned first, then coat. So if rain, then coat. So for contrapositive, the coat will come first, and then the rain. So opposite of wearing my coat would be, if I'm not wearing my coat, then it's not raining. So that's how we can make the contrapositive of a non-mathematical statement, for example. So how to explain the equivalence of an implication and its contrapositive? And we're going to appeal to some old-fashioned Venn diagram types. So consider the case when the statement that A implies B is true. If that is true, and that's the case, then case A must fall entirely inside of case B. And I'll illustrate this using a type of Venn diagram. So if an event is A, that implies it's B, that can only be the case and can only be always true if all of A is included inside B. So for example, A could be England and B could be the United Kingdom. If I live in England, then I live in the UK, because England A is contained entirely within B, which is representing the UK. So let's just consider this now. In particular, let's consider the region representing not B, so anything outside of B. So if B is this, not B will be everything outside of this ellipse, but inside of this big rectangle on the outside. So I've coloured in not B in this light blue colour. So what do we notice that's not in B? Well, because A falls entirely within B, then if we're looking at what isn't B, then anything not in B is also not in A. So this region here where it's not B, obviously is not going to be A either. So that shows that if A implies B is true, then not B will indeed imply not A. That will also be true too. So that's showing that if A implying B is true, its contrapositive statement will also be true. But what about if this implication were false? So let's get rid of this and think about what if A implying B isn't actually true? What if that's false? Well, here, in this case, at least part of case A must fall outside of case B. For example, like this. So here, I can't say with all certainty that A implies B. For example, if I'm talking about this part of A, then that part of A is not part of B. So A implying B in this case isn't always true. So let's just consider this diagram in a bit more depth. So let's consider the region representing not B. So again, if this ellipse is representing B, then not B will be anything outside of this ellipse, but still inside the rectangle, which again I'm colouring in this light blue colour here. So that's not B on the outside. So the contraposition of A implying B would be not B, would imply not A. But we can see here that if we have a look at the region not B, that can't imply not A too, because some of A is in this region that doesn't include B. Some of A is contained in not B. So in other words, because some of A is outside of this B, then anything not in B may actually also include some of A. So we can't say that not B implies not A either. So therefore, if A implying B is false, then we can say that not B implies not A is also false. So that's an illustrative way of explaining the equivalence of an implication and its contrapositive. So when is this contrapositive idea actually used? Well, first of all, it's when we're proving implications. For example, if A, then B. It's also used when cases A and B can be considered as binary. For example, if we're talking about odds and evens, a number's either odd or it's not odd. It's odd or even. Or it might be multiples of 5. If a number isn't a multiple of 5, or it is a multiple of 5, it's one or the other, and so on like that. And as well, we'd only really consider using it where a direct proof is pretty much difficult, or dare I say, impossible. So let's have a look at an example. So let's imagine we wanted to prove that for all n being any natural number, if n squared is even, then n is even. So would the contrapositive be of use here? Well, yes, it would be, but let's just check. So, is the statement an implication? Well, yes it is, because it says if and then, so it's an implication. Are the cases binary? We're talking in terms of evens. It's either even or odd, it's one or the other, so yes it is binary. Is there no easy direct proof? Well, if n squared is even, then we can say n squared equals something 2k, where k is a member of the naturals. But to show that this is even, could I square root 2k algebraically? No, I can't. It's not easy at all. So in that case, I'm going to abandon ship and think actually maybe the contrapositive would be easier after all. So let's write now this statement in its contrapositive form. So n squared is even. N is even. This is what we want to prove. The contrapositive of this is as follows. N squared is even implies n is even. The contrapositive is we start with n first. Opposite of even is odd. So if n is odd, n squared is odd. And like we mentioned before, if we can prove a contrapositive, we've proven the initial statement, because the contrapositive and the initial statement are logically equivalent. Now this is much easier to prove. So let n equal 2k minus 1. So I'm using a representative of n as 2k minus 1, where k is a member of the natural numbers. So in that case, n squared will be 2k minus 1 all squared. Now let's square this out as we would do any brackets, even at GCSE. So 2k all squared gives us 4k squared. We take the product of what's inside the brackets and double them. So 2k multiplied by minus 1 is minus 2k. Double that gives us minus 4k. And finally, minus 1 multiplied by minus 1 gives us plus 1. And now we want to prove that this is odd. And so an odd number is either 1 more or 1 less than an even number. So I'm going to deliberately factorise out a 2 from here. If you're thinking I could factorise out a 4, well yes I could, but by factorising out a 2, I'm emphasising that what goes inside here, this all must be even, because I'm making it a multiple of 2, which by definition is even. So I can say it's 2 lots of 2k squared minus 2k plus 1. So this is a multiple of 2 plus 1. So which is odd. So therefore, since we've proven when n is odd, this implies n squared is odd, then by the contrapositive, we've proven the initial statement too. We've proven that if n squared is even, then n must be even. Let's have a look at a second example. Prove that for all x being natural numbers, if x squared minus 6x plus 5 is even, then x must be odd. Again, let's do a little contrapositive check. So again, it's the same as before. It's an implication, it's an if and then statement. The case is a binary. Again, we're talking about evens and odds. Is there no easy direct proof? Well, again, if this is even, I'd have to write this in the form of 2k. Could I show that the square root of 2k is odd algebraically? I really don't think I can. So this again, there's no easy direct proof. So let's write the initial statement in its mathematical form. So x squared minus 6x plus 5 is even. And the statement is saying this implies that x must be odd. Let's write the contrapositive form of that. So again, we just switch the order and write the opposite of what these things are. So put x first, switch the order. X, opposite of odd is even. So the contrapositive means if x is even, that should imply that x squared minus 6x plus 5 is the opposite to even, is odd. So can we prove this? Well, if x is even, just let x equal some multiple of 2. Call it 2k, where k is a member of the natural numbers. Then if that's the case, x squared minus 6x plus 5 equals 2k squared minus 6 lots of 2k plus 5. Now 2k all squared is 4k squared, then minus 6 lots of 2k means minus 12k altogether, and then we can add 5. So now what we can do is we can write this in terms of multiples of 2, and then we can prove that we're going to have something extra on the outside. So let's see how we can do this next. So let's factorise out a 2 to emphasise we're going to have something which is an even number. So 4k squared, inside the brackets we can put 2k squared, minus 12k. If we half minus 12k we get minus 6k. And as well, I'm going to put 4 inside the brackets by doing 2 multiplied by plus 2. Now 2 multiplied by plus 2 gives us 4. We need 5, so we need to add an extra 1 on the outside. So this thing here is a multiple of 2, which is even. Therefore, when I add 1 to it, we can say this is odd. Now we just write closing statements. We've done the hard work. So, therefore, we've shown if x is even, then indeed x squared minus 6x plus 5 is odd. So by the contrapositive, if x squared minus 6x plus 5 is even, we've proven that x would have to be odd. And that's it. So I hope you found those two examples useful and illuminating in terms of how this contrapositive trick really can be used to simplify things. But don't worry if you're thinking you need to learn and revise this for your A-level, you don't. I've just included this here for an extra bit of learning in case your curiosity's been raised by what I may have mentioned in class. So thanks for listening if you have. Please do consider subscribing if you haven't done already, and I'll hopefully see you all soon. Take care and goodbye for now.